Let's start lecture 25, and the course is Corrosion Protection Methods. And today's topic, it will be based on the broad topic, which is change in environmental factors and associated corrosion protection. So we have started discussing on different aspects like removal of corrosives, and there we talked about removal of oxygen, removal of chloride ion, as well as removal of strong oxidizers. So those cases we can actually reduce the corrosion rate, and we have also seen how it happens. But removal of those corrosives and associated decrease in corrosion rate, that relates more toward for the active metals, which shows only activation polarization, as well as that metallic polarization part would not go to passivation. Okay. So then definitely we can see a very good amount of corrosion protection or a decrease in corrosion rate greatly if we actually reduce those corrosives. In fact, sometimes those are actually oxidizers. For example, Fe3 plus or copper 3 plus, those are strong oxidizers. So if we reduce, definitely we can reduce the corrosion rate for active metals. Now we started talking about effect of chloride ion on the corrosion behavior, and in fact we started talking about effect of chloride ions on the enhancement of crevice corrosion. The same mechanism holds true for pitting corrosion, okay, because the chloride ion actually leads to metal chloride formation near the vicinity of crevice, and then accordingly there would be hydrolysis, and then hydrolysis would lead to generation of hydrogen ion, and that hydrogen ion will break the passive layer. And we started talking about the effect of chloride ion on the passivity. So today we will try to see how chloride ion influences the passivity of a metal. Okay. So now if we talk about a subtopic, which is effect of so then we would realize that why this is important aspect and why chloride ion removal helps in achieving passivity and maintaining a low corrosion rate. Now if we talk about a typical active passive metal, let's say this is my potential versus log I plot. Let's say this is in ampere per centimeter square. Now if we try to see the typical active passive metal, so this is a typical active passive metal, and where you have this dotted line, this is the dissolution part, let's say some metal N plus M releasing electron becoming ion, so that's a dissolution, and this is my polarization plot in the anodic side. This is my I0, which is exchange current density, M I0 of metal dissolution or metal deposition on the metal surface, and this is my E equilibrium for metal. And if we go back to earlier lectures, you would see why this passivation happens, what is the mechanism for passivation. Now once it reaches to a particular current density, this is the current density, we call it I critical, or in short we say IC, or instead of making IC, let us put I crit, because IC also reflects the current density corresponding to cathodic current. Now cathodic polarization. Now if we talk about I critical, so larger the I critical, it is difficult to achieve passivity for that metal. Now once we cross the I critical, immediately the oxide that is forming on top of that metal will cover up the entire surface and it will achieve passivity. And then we would go to current density, which is I passive. It is termed as IP, and then this is potential corresponding to EP, which is the passive current density, passive potential, and then it will maintain almost a similar current density over a very good over a large range of current potential. So, from up to this potential, it will maintain passivity, and that current density corresponding to that passivity is IP, and this is the potential which is called transpassive. You can say ET, which is the potential corresponding to the start of the transpassive zone. And if we consider that to be the dissolution of that metal, then rapid dissolution happens here again. Okay. So, it goes through active zone. So, that means if we mark different zones, so this is active zone, then this particular part which is passive zone, and then beyond that we call it transpassive zone. Fine. Now, what sort of behavior that metal will show in a particular environment, or let us say in a particular environment containing some oxidizer or a chloride ion, that will be decided based on what will be the influence on this particular polarization plot, or how the cathodic polarization line interacts with this anodic polarization plot, which is showing active passive behavior. Why it is active passive behavior? Because when we start the polarization, then it will first go through active zone, and it will pass through active zone, and then it will achieve passivity, and then again it will break into transpassive zone. So, that is what it is called active passive behavior. Now, let us say if cathodic line interacts, the polarization line for this metal, let us say it interacts here. If it interacts here, so this is my cathodic line. So, this is my cathodic polarization line. Right? And we can corresponding to IC, which is cathodic polarization current density, and this is I 0 for the cathodic reaction, and this is E equilibrium for the cathode. So, if we consider a hydrogen reaction to be my cathodic reaction, or let us say iron is present, ferric ion is present. So, that time cathodic reaction would be Fe3 plus E equal to Fe2 plus. So, this is a strong oxidizer. So, if the appearance is like that, then the corrosion potential would be this point, and the current density corresponding to corrosion rate is this one. Right? Now, if it cuts here, so let us say the cathodic line cuts the polarization line for metal dissolution, like the red one cutting the green line. So, then this will be my corrosion, I corrosion, and you can see that this is equal to IP, or the passive current density. Now, if the red one is the cathodic polarization line, then the corrosion rate would be corresponding to passive current density, and it is lower than the I core corresponding to the first polarization curve. So, if we talk about the polarization curve for this, I am talking about this polarization curve for the cathodic reaction. So, then, and if we consider it to be 1, and if this one is corresponding to 2. So, then definitely I could see that I core 2 is less than I core 1, just because of the interaction, the very interaction of cathodic polarization line with the anodic polarization line. This is based on the mixed potential theory. Now, when we try to see the polarization curve for these two situations, we will have typical plot like active passive transition plot. In another case, we will see spontaneous passivity plot. Okay. So, now in case 1, which is talking about corresponding to I core 1, the polarization plot would be, this is E volt, so in first case the plot pattern would look like this. This will be the plot pattern. If we go from a very low potential, let us say I start from this point is my start of polarization, then I will go like this. So, if I try to find the polarization plot, so the black one will go like this, move like this, and then move like this. So, the black line would be the polarization plot for the case 1. Okay. I have just shifted it little on the left side, because just to identify the actual experimental plot with the anodic polarization line. Fine. So, then corrosion rate, what we can find out is we can draw a Tafel slope here, and this will be my I core, this is I core 1. Okay. And in case of the case 2, polarization plot would be okay. So, this polarization plot would be, if we try to see, like this. Okay. So, it will be further above like this. Okay. So, this will be my I core 2. This will be two typical polarization plot. Here we call it spontaneously passive, and this is called active passive. If we leave the material in that condition, okay, so then in one case, in case of case 1, your corrosion rate would be at this location, and in case of the case 2, your corrosion current density would be at this location. Fine. So, now how do we get it? So, you can do it like this. So, this will be my corrosion current point. Now, question is if we leave it there, but if we forcefully take the potential upward, definitely you will achieve this curve when you do experimental polarization or dynamic polarization. If you do, you will get such kind of plots. Now, but if you leave it like this without having any external influence of current, then definitely your corrosion potential as well as corrosion current density will be at the location where I have made this circle. Okay. Now, question is, what happens if we add chloride in this particular active passive metal? So, generally what happens if we add chloride, this particular range, we can say del EP or del EP passive, this shrinks. So, that means this transpassive point goes to the downward direction or it reduces. This I critical shifts to the right, okay, and this current I passive also shifts to the right. This IP, what the passive current density, shifts to the right. So, that means ET, this particular potential shifts to lower end, that means transpassivity is achieved quicker at a lower potential. IP, what used to be at a no chloride condition, that IP shifts to right, that means I passivity current density goes up as well as I critical goes up. Now, what would be the influence of that? So, let us say if I try to see the chloride influence, so what happens? So, if this is my typical plot, if this is the typical plot, if we have chloride first hand, it goes up, second part, let us say we further increase the chloride content or the concentration, it further goes up. You see this potential gradually decreases, this particular current density gradually increases, and this IP gradually increases, sorry, I critical. So, now 3 effects. So, that means this is C3, this is C2, this is let us say C1 or no chloride. As we go ahead with the addition of chloride, this will be the influence on the anodic passivation plot or polarization plot. So, 3 effects, one is ET goes down or delta ET goes down, or we can say passive potential range shrinks. Okay. So, that is bad, because if the passive potential range shrinks and if there is a little fluctuation in the cathodic polarization equilibrium potential, so that if there is a little fluctuation, then it can take it to passive transpassive zone. So, that is the problem. Okay. So, this is bad for the passive metal. Second part is IP, which is the passive current, increases as we increase the concentration. So, third is, and what is the disadvantage of it? As IP increases, definitely the corrosion current density corresponding to the cut point between the cathodic polarization line and anodic polarization line, if that increases, corrosion rate definitely increases. So, that is also bad. So, that means it is showing higher I-core if cathodic line cuts the passive zone. Okay. Definitely. So, that means increase in corrosion rate. Now, third is I critical increases. Now, what is the relation between the poor corrosion performance of the metal with passive behavior if I critical goes up? If I critical goes up, then the material, when it goes from a low potential to high potential, it is very difficult to achieve passivity, and the passivity can only be achieved if the cathodic polarization line cuts the anodic polarization line crossing the I critical point, then only we achieve passivity. So, then this is also bad, because this does not allow passivity to achieve. So, all those 3 cases happen with increase in chloride ion concentration. So, that means increase in chloride ion concentration is actually acting bad towards that, towards the corrosion resistance of the material with passivity. Now, let us understand little bit on this. So, with the help of mixed potential theory, let us understand what happens if we decrease the ET. I will take two instances, and one case is this, another side by cases. Let me put it like this. Let us say, though I have drawn two curves side by, let us say I critical does not change and IP does not change. Just for identifying these two plots, I have drawn the blue one on the little right on the with respect to the black one, but they are actually merging. If we merge right now, then it will be difficult to distinguish. So, that is what I have marked the blue one little on the right side, but I critical remains same. So, these 2 points just for marking, but they are almost on the same point. So, I critical, the condition is I critical does not change, as well as I passive does not change. So, these are two conditions, but ET reduces. So, let us say the cathodic polarization line is here. Okay. Just for understanding, let us see. So, let us make it little on the upside. If the cathodic polarization is here, and if we consider this is, let us say, case 1, and let us say this is case 2. Case 1 and case 2. So, this is my IC, or the cathodic polarization current density. And if we could see that in one case this is cutting in the passive range, and the second case it is cutting in the transpassive range, and that happens. So, in case of case 1, corrosion rate is I passive, I core equal to I passive, and in the second case where the cathodic polarization line cuts the plot corresponding to case 2 in the transpassive region, which indicates the corrosion rate at this point, this is called case 2. So, let us say this is case 1 is nothing but less than I core case 2. Okay. So, this happens only because there is a reduction of ET, and ET is what? Which is the start of transpassive zone, and here which is the potential corresponding to transpassive zone, and in the second case this is my ET 2 and this is for 1, case 1. So, we could see that if there are no changes in I critical or IP, but there is only one change which is related to E transpassive. So, and E transpassive reduces because of increase in chloride ion concentration, then I could see that the passivity is broken. In case of case 1, passivity is maintained, but in case of case 2, passivity is not maintained, fine, and then situation becomes bad because the corrosion rate corresponds to transpassive, which relates to a rapid dissolution of the metal, and passive layer is destroyed. So, that is bad. So, that is what I meant to say, that when ET reduces, passive potential range shrinks, and as well as we have problem in maintaining passivity. So, this is one such instance. There could be instance like, let us say this potential varies. let us say there is a suddenly there is some increase in oxidation concentration, oxidizer concentration. So, if we have increase in oxidizer concentration, if this happens, okay, so this is related to ET reduction, delta ET shrinking, okay. So, those cases I get such situation, but if there is change in oxidizer concentration, so that means let us say if I consider Fe3 plus, if this concentration goes up and if I follow the Nernst equation, and since here only one electron is involved for this reduction, okay. So, if this goes up, this potential also goes up. So, that means this particular point which is corresponding to E equilibrium oxidizer. So, if this goes up, so let us say it goes up here, and let us say that time the condition is these two potential. So, this is one potential and this is very close to it, okay. Let us say here ET is corresponding to this plus, okay. So, that time if we see the plot pattern, it will follow its, let us say if we do not change the concentration, so this green line would follow, and then for both the cases, just a minute, let me just draw it separately, then you would understand. So, let me just draw it separately. What happen if we increase the oxidizer content? So, this is one situation where oxidizer content does not change and only ET changes, and we are going to get higher corrosion rate, because the interaction point between cathodic polarization line and anodic polarization line, it is happening on the right side as compared to I passive or the passive zone. Passive zone is broken. Now, in this case, if we try to see the polarization plot, okay. So, let us say one plot is like this, and another plot just like the previous one. I critical does not change, but ET changes. Okay. E transpassive changes, and this blue one and the black one, this both the plots, these 2 points are on the same point, because just I have drawn on the right side just to have identity, but they are actually merging. That means these two conditions are holding true here also. I critical does not change, IP does not change. Now, if the cathodic polarization line is like this, okay. So, that time I have some concentration, let us say C1 for oxidizer, okay. And once oxidizer content increases, this particular potential goes up. So, let us say the oxidizer concentration is such that the potential reach to this level. So, the new polarization plot would be here. So, if we draw it in red color, so this will follow this track, fine. Now, this is C2 oxidizer, and C2 is greater than C1, and I could see that if Fe3 plus is the oxidizer, so in one case C2 is the concentration of Fe3 plus which has increased, rest all remain same. And here also you could see that if we stay at C1 and if we add chloride into it, and if there is only change in the ET, there is no change in I passive as well as I critical. So, this is my I critical and this is my I passive. So, these two do not change, only change is this ET has reduced to another new ET because of the chloride ion, and at the same time there is a change in concentration of oxidizer. So, that means in case of black plot, what are the two conditions? So, these two conditions holds true, I critical and IP do not change, but ET is at ET case 1. So, this is ET case 1 and this is for black one, and the blue one. So, I critical case 1 is equal to I critical case 2, IP case 1 equal to IP case 2. So, these two conditions are holding true, but ET case 2 is less than ET case 1 because of addition of chloride ion concentration. Now there are the condition what is there, if we have, this is my corresponding equilibrium of cathodic reaction for both the cases. So, if C equilibrium for the cathodic reaction, then the corrosion rate for both case 1 and case 2. Okay. So, this is case 1, this is case 2. Okay. So, are same because the cutting point is at the same location between the polarization plot of anodic polarization plot and cathodic polarization plot. Now, situation is changing. This is one condition, the condition 1. So, this is basically condition, let us say condition A, where oxidizer concentration is equal to C1. Now, we have condition B, where oxidizer concentration move to C2 and where C2 is greater than C1. Definitely, I will see that the potential corresponding to equilibrium potential, this is C1, this is C2, this is for all for cathodic reaction. Okay. Same reaction is happening, which is if we consider Fe3 plus. So, Fe3 plus electron is Fe2 plus, same reaction for both the cases, fine. But Because of the concentration increase of the oxidizer, the potential goes up, and this is shown as per Nernst equation. This is my Nernst equation, what has been shown here. Now, this case, the polarization line is actually cutting the case 1 polarization line or anodic polarization line at IP, whereas in case 2 it is cutting at this point. So, let us say this is I core 2 and let us say this is IP, still IP, which is I core 1. Okay. Now, this is for concentration C2 and this is for concentration C2 for the oxidizer. Now, we could see that though in case 1 where in condition A where concentration of oxidizer is maintained at C1, both the conditions of high presence of chloride as well as no presence of chloride, and there is only one change, which is the ET decreases, I could maintain the I passive all the time, and that will be my corrosion rate. So, that means both the situations with chloride or without chloride will have a low corrosion rate and maintain at passive current density, because of this very interaction of the cathodic polarization line with the anodic polarization line. Now, once we increase the concentration of oxidizer from C1 to C2, then the equilibrium potential for the cathodic reaction goes up and corresponding cathodic polarization line will interact the anodic polarization line differently because of the chloride presence. In case of situation where chloride is present, so that time it will interact at transpassive zone, and where there is no chloride it will interact at the passive zone. So, in one case corrosion rate will corresponding to the previous cathodic previous I passive, but another case it will cut in the transpassive, and when something is cutting in the transpassive zone, that means cathodic polarization line is cutting in the transpassive zone, it actually breaks the passivity, which is not good. It will have a rapid dissolution, and you could see that the I core 2, this particular current is on the right side than the as compared to I passive. So, it is in the log scale. So, the corrosion rate increases rapidly. There are two disadvantages. One is, of course, the rate of dissolution increases because of the increase in corrosion rate, corrosion current density, but at the same time it will no more maintain the passivity. Okay. So, in this situation condition 2, I core condition 2, when the concentration is C2 is greater than I core, which is nothing but IP case 1 case 2 and concentration C2. So, this condition will be felt by the metal, and this is first part, corrosion rate increases, and the second situation would be passivity will be broken, since cathodic polarization line cuts anodic 1 in the transpassive zone. Fine. And in fact, this leads to serious pitting. Fine. So, that means you could see that what is the disadvantage of decrease in ET because of the addition of chloride. So, we will discuss about the effect of increase in I critical as well as increase in I passive in our next lecture. So, till then, thank you.